Since the dawn of civilization, keen watchers of the night skies have noticed the changing positions of 5 points of light in relation to the other stars. The ancient Greeks called these wanderers, planetes, from which the word planet, of course, is derived. The Greeks noticed that the motion of planets was confined to a narrow zodiacal band that was centered on the sun's motion and passed through 12 or more constellations. This can be explained by the fact that all the planets orbit the sun in roughly the same plane. Now, if you look at the chart I put up on the screen now, you can see the bar chart shows the orbital inclination for the planets. By definition, the inclination of the Earth's orbit is 0, and the smallest values of I confine the planets to a narrow zodiacal band in the sky centered on the ecliptic. Okay. So you can see that Mercury's orbit has the greatest inclination as compared to the other planets. From night to night, the planets move slowly eastwards, but ancient astronomers noticed that occasionally they appear to travel backwards from east to west in either a loop-the-loop or a zigzag motion. This is known as a retrograde motion. Now, in the diagram, the position of a superior planet, such as Mars, is shown at weekly intervals. Now, retrograde motion can now be explained in terms of the fast-moving Earth overtaking the superior planet on the inside of its orbit, but this caused huge problems for ancient astronomers. The dashed lines indicate limits of the zodiacal band. These are 8 degrees, roughly, either side of the ecliptic due to the relatively large orbital inclination of Mercury. Okay. Make sure, of course, that you know how to define an ecliptic. Okay. Now, the optimum place in its orbit, and I've marked it with a tick, for a planet to be observed under the best, darkest sky conditions depends on the planet's orbital position compared with that of the Earth, and the orbit's shown as a blue dashed line. Now, I'm going to consider key positions in the orbits of inferior and superior planets. So, an inferior planet, as we're looking at now, such as Mercury, is best observed when it appears furthest from the Sun in the morning or evening sky. This is at or close to greatest elongation when the angle Sun planet Earth is 90 degrees. Whereas a superior planet is best observed at or close to opposition. At this point in its orbit, the planet is closest to Earth. At its brightest and opposite the Sun in the sky, it is possible to observe the planet all night long with the highest resolution. Now, when it is at inferior conjunction, an inferior planet may undergo a transit of the Sun's disk. Transits, however, are extremely rare events due to the orbital inclinations taking the planet either above or below the Sun in the sky. A more common event is an occultation, in which a planet may temporarily obscure a distant star as it moves in front of the star for a few moments. Now we're going to talk a little bit about the apparent motion of the Sun. Now we're going to leave the planets and look at the Sun's eastward journey across the celestial sphere during 1 year. Of course, the Sun isn't really moving. Its apparent motion is due entirely to the orbital motion of the Earth and the constant 23.5 degree tilt of the Earth's equator to the ecliptic. The position of the Sun on March 21st marks the 0 of right ascension at the first point of Aries, where we use that sort of ram's head symbol. The graph shows the celestial coordinates of the Sun over the course of the year. This symbol denotes the first point of Libra, where the Sun returns to the southern hemisphere on September the 23rd. Okay, so I'm just going to give you a few tips. So you should be able to relate the position of the Sun on the celestial sphere at key dates in the year to its location above key latitude on Earth, of course. For example, on June 21st, the summer solstice, the Sun's celestial coordinates are 6 hours, 20 23.5 degrees, and it lies directly above the Tropic of Cancer.